So let me first of all start with two obvious comments. One obvious comment is that conformal field theories are quantum field theories. So everything you learned about how vectors transform, how tensors transform, how anything transforms is also true. We did not enter a different parallel Twilight universe where things work differently. Conformal field theories are particular examples of quantum field theory. Okay? The second comment / advice I want to make you is whenever you want to understand what transforms, what doesn't transform, don't work only with the left-hand side. Don't try to write some expression like some correlation function at some points and then start putting tildes on the left and on the left-hand side everywhere, on tildes on x's, on tildes on x's, and you will just get confused. Write also what the right-hand side is. What is the result? And try to see, is it invariant or not? The result as I try to do some transformation, like x to lambda x or something like this. If you start transforming everything, you are doing nothing. Okay? So if you say that instead of considering 2 points separated by 1 meter, I'm going to consider points separated by 100 centimeters, I'm doing nothing. Right? So be careful not to change, not to make a dilatation and then change the metric so that you are effectively doing nothing. Right? All theories are invariant under changing 1 meter to 100 centimeters. This is not a conformal field theory. Okay? Is this okay? Now, having said that, there are several ways to think. That's why sometimes this thing is prone to confusion. Because you always have this active or passive transformation, right? So, if I have, say, $100 in the bank and I have some more money, I can say I have now $140. Or I can keep 100 and say I have 100 euros. Right? So, I mean, I prefer to think in terms of amount. Some people might want to say I always have 100 and they change the currency. And that's fine also. Right? You can do it. But just be aware that, of course, there are different, totally equivalent ways of thinking, depending on whether you want to adopt a more passive or more not passive approach towards thinking about exactly the same thing. And of course, because different people think in different ways, this is a subject that is very prone for confusion if one starts imposing one's way of thinking upon someone else. So if you have your own way of thinking, provided it works, that is, you write the right-hand side, not just the left-hand side, and start putting tildes everywhere. You write the right-hand side, you do a transformation, and you compute again the quantity, and you see that they are the same, or they transform as they should, you should be happy. It's okay. Anyway, let me tell you one consistent definition. A conformal field theory is a theory for which if you have a generating function of all your correlation functions, in a given space-time given by a metric G that is fixed, it's not a dynamical metric, and if you want to relate it to correlation functions in a new space-time whose metric differs by a local dilatation, which is called a Weyl transformation, they are the same. All you have to do, you also have to shift the currents because they are coupled to an operator that has some dimension. By the way, yesterday in the lecture, I think I had a typo. I wrote the wrong sign here. So if you have your notes, please fix. And this definition is a very elegant, very short definition of what a CFT is. It doesn't depend on a Lagrangian. You can obtain this by a path integral, or this can be your definition of your theory, if it's a consistent generating function. And what is it equivalent to, and what does it imply? It is equivalent to saying that if you compute correlation functions in a given space-time, or in a space-time that is related by a Weyl transformation, okay? Then there is a simple relation between the two that just takes into account the local dilatation at each point of the original space. It's okay? This implies, notice that I was careful writing these arrows with 2 signs or just one direction. This implies the following. It implies that if now you don't change space-time, so again, now we are in flat space. But we consider correlation function between points at position x1 up to xn. Or a correlation function in the same space, but at positions x1 tilde up to xn tilde, where x goes to x tilde under what's called a conformal transformation, which is a transformation where if you compute the line element, distances are transformed in this particular way. If you do this, and if you compute the correlation function at these positions or at these other positions, you change the positions, the relation between the two results is just this. Why is it true? Because to say that I did a dilatation, or to say that I did nothing, but now I measured my metric with a factor lambda more, is equivalent. Right? It's exactly the same. It's like saying that it's exactly the same examples I was giving in the very beginning. Okay? So to say that I kept my metric and I changed my points, or I kept my points and I changed the way I measure how they are distant from each other, it's exactly the same. So if we stick only to RD, here is a prediction for how correlation functions in the same space-time are related. If on the other hand we want to do another kind of predictions, which is to say how to relate correlation functions in different space-times, here is the formula you have to use. Okay. Still, I want to do two examples, even though I suppose that by now this is clear, but I still want to insist on two simple examples. The examples are those that I wrote here. I will, of course, not erase this blackboard because it was written before we start. So let's start with this example, where we have here two spacetimes, flat space, and a wrapped flat space, where each point in flat space I measure distances with a weight that is 1 over the distance of this point from the origin square. Okay? Well, let's consider this first example. Okay? Then what are we writing by that? We are saying that, okay, so let me first write that O of x, O of y. Let's start with the following correlation function. So let me write the right-hand side. As I said, it's very useful to always write. So it is just the distance to the points to some power 2 delta. This is what this correlation function is in flat space. What is the correlation function, the same correlation function at the same point, x and y, if instead of considering flat space, I consider the metric 1 over x squared dx mu dx mu? Well, according to the rule that I wrote there, I should write x squared to the power delta, y squared to the power delta, these are these factors of omega, times the correlation function O of x, O of y, in the space where the metric is just dx mu, which is just RD. That is, we get just x squared to the delta, y squared to the delta, over x minus y to the 2 delta. But this is, of course, the same, this is equivalent to computing the correlation function between a point which was inverted, so let me put x mu over x squared, y mu over y squared, in the original metric RD, right? That is, here is my unit sphere, and here is a point x, and here is a point y. I have two ways of thinking. Either I say that under this inversion, I invert the point, so let's see, x is the one that is closest, goes somewhere here, and y is a bit further away, it goes somewhere here. So this would be y tilde, x tilde. And then I keep the same metric g going to the same metric g. Or, equivalently, I say, and it's physically exactly the same thing, I keep the same point x and point y, but I say that my metric now is rescaled, and distances now, points that are very far away from the origin, their distance is effectively very small. And if 2 points are very small, their distance is effectively very large. Okay? Is it clear? I mean, it's absolutely equivalent. Of course, if I say that I invert the points, but I also think that the metric now is also 1 over x squared times the metric, the distance didn't change, nothing changed, it's exactly the same physics. It's like changing 100 euros to $140. I mean, it's the same. You are not changing anything. You are doing 2 transformations that undo each other. So this should be just equal to this, and now this is something we can check. We know this result, we can apply inversion, and we saw that under inversion, indeed x minus y squared under inversion went to x minus y squared over x squared y squared. So if you plug this transformation under inversion of this formula, indeed it works. Okay. Okay. Is it clear? Please, is it clear? Yeah? Let me do a second example where we now change spacetime. Okay? Let's do an example where we change spacetime. So this is example 2 here. We start with flat space that I wrote here in spherical coordinates. So I start with I will repeat what I wrote there in point 2. So we start by writing flat space in radial coordinates, where a given point is at some distance r and in some direction n. Okay? Where n is a unit vector that tells me what is the direction. Such that I can write my metric as dr squared plus r squared times the metric of a unit sphere of d minus 1 dimension. Now, if I write r to be e to the tau, just a parameterization, this becomes e to the 2 tau times d tau squared plus the metric of the sphere. So this spacetime, which is the metric for Rd, and this spacetime, which is the metric for a cylinder, which is r times a sphere. You see, if it's r times a circle, it's clearly a cylinder, right? It's what we usually call a cylinder. There is a circle and then time. So this is a d-dimensional cylinder. So r times a sphere, which is just d times square plus the metric of a sphere, are indeed related by just a Weyl transformation, omega squared, okay? Which is a function of tau, and then it actually only depends on tau, the coordinates of my point. Is it okay? So the way this works is if you have a point with some r and n, and you have some other point with some r prime and some other vector n prime, how is it mapped into our cylinder? So let's draw the cylinder here. So this is the sphere, the circle. So this circle is my attempt at drawing a d-dimensional sphere. Of course, I can only draw it if it's two-dimensional. And this direction here is tau. So this line here would be a line with tau, and here we would have a line who was closer to the origin, tau prime. So this would be tau prime. Here it would be tau going to minus infinity, which in this language means r going to 0. Right? And here r going to infinity is the same as tau going to infinity as well. So tau going to minus infinity is the origin, was the origin in flat space. And tau equal to plus infinity was infinity in flat space. And the farther you are from the origin, the higher you are in time. And you could indeed have some point here with some vector n prime, and here some other point with some vector n. So this would be your point y, and this would be your point x. If this is the point x, and if this is the point y. Okay. So now let's do just a simple exercise to see if the correlation function for points in a cylinder, in a conformal field theory, if it gives something reasonable or something that clearly doesn't make sense. Well, let's try to compute the correlation function in the cylinder. So let me write an equation. Well, let's use the relation that we have there. So the correlation function for a point O, let's use this as our starting point that we know how to compute. So the correlation function O for a given point which is specified by tau and n, and another one at some tau prime and n prime, in the plane, in RD, okay, is equal to omega of tau to the power minus delta, omega of tau prime to the power minus delta, times the correlation function of the operators in a space which is related by RD, in this space, which is the cylinder. Okay? So again, don't be confused. The cylinder is what plays this role, right? The cylinder is the d tau square plus the sphere. If you multiply it by some omega, you go to flat space. Flat space is on the left-hand side. Okay? So you see the equation there. So you have the cylinder. You multiply by this e to the 2 tau, you get the metric in flat space. So this is the cylinder. This is flat space. The sign is minus. The sign is minus there. Everything is okay. This is what we want to compute to see how it looks like. This is what we know the result. The result is there. So this is just 1 over the 2 points, e to the tau n minus e to the tau prime n prime square to the power delta. This is just e to the minus tau delta tau, and similar for the other one. So it's a simple computation. I mean, there's almost nothing to do to see that this quantity here is therefore equal to 1 over, so I divided and I put these factors inside the delta and I computed this square, and the result you get is 2 cosh of tau minus tau prime minus 2 n dot n prime to the power delta. Okay, so you see that the way the computation started, something nice happened here. Let me emphasize it, which was that you had tau here, you had tau prime here, you had exponential of tau here, exponential of tau prime here. Tau and tau prime were appearing in a very random way. But at the end of the day, what is happening is that all that appears is the difference, tau minus tau prime. Exactly as we expect for any theory that makes sense if we are to define it on a cylinder which has translation invariance. So what we are saying is that it only depends on, if we put 2 points separated by some delta tau, all that matters is this delta tau, which is tau minus tau prime. Okay? So everything is consistent, we are getting sensible results, and this will be the correlation function of a CFT in a cylinder. It's a very non-trivial prediction, you see. I mean, you are telling someone to do, say, Monte Carlo, and put some lattice in a cylinder and compute 2-point function, or do Monte Carlo in a plane, and you are telling that the 2 computations should give the same. It's a very non-trivial statement. If this works, the theory is conformal. If the theory is just some scale invariant or some simpler theory, some crazy thing like this would not work. Okay. Very good. Any question before we move on? Are the confusions clear? Is it okay? Is it consistent? Everything makes sense? Okay, if not, please come and talk to me at the end, and I can try to help you out, clarify some issues. Okay. Then the next thing we did was ask ourselves, okay, so there are transformations that are particularly nice, that all they do in practice, they are equivalent to a wild transformation. We can think of them as either transforming the points or as keeping the points and changing the metric, like we were saying here. Either we keep these points and change the way we measure their distance, or we transform the points. Conformal transformations in D bigger than 2, there are not that many. There are a few generated by translations, special conformal transformation, rotations, and dilatation. And we actually saw that if you have Poincaré plus inversions, you more or less generate the full group. So it's very powerful and very useful to just check inversion. If inversion works, you are done. If inversion doesn't work, you should still think a bit before ruling out the theory, but inversion is always a very good check. Now I want to make just a few simple comments about these transformations to show you that they look a bit random, but you could hardly write anything else. So let's start with the simplest ones. Commutation of a rotation with something that has a vector index. I mean, it doesn't matter what this something is. Any vector, if you rotate it, you rotate the index. So all this equation is telling you is that you know how to work with indices. That if you apply a rotation, this index is changing. I mean, that is why this relation for P or for K, they are exactly the same. Just replace P by K. P is a vector, K is a vector. It's just telling you that if you rotate a vector, you get a vector pointing in some other direction. Here you have a tensor. It has two indices. So if you ignore the second index, and you think just of M alpha, you get the same thing as here. And this would be, for example, the first term here, and now you have a second one similar to it. And then you rotate the second index, which gives you two similar terms. So the one for M would also not be anything else. It's just a statement that you know how to rotate the index. The statement that you commute dilatation with P and get P itself, it's also obvious. It's just the statement that if you do a dilatation, the vector by which you translate increases. You translate by more if you do a dilatation. The fact that K and P are related by a plus and a minus sign, it's also natural, because remember that. What was K? K was a translation after doing an inversion. So you can think that you have your origin, and you have infinity, and P and K are conjugate to each other under this inversion. So whatever happens in some space with respect to P, happens in the inverse space with respect to K. But doing a dilatation is making the points close to the origin more separated and the points close to the origin more dense. And conversely, an inverse dilatation that is shrinking the points from the point of view of infinity is working as a dilatation. Because of that, you ought to have a minus sign with respect to conjugation by the dilatation. K with P, it's, I think, a bit harder to argue. But one thing you could say is that if you have indices mu and nu, the only two tensors you could write are the metric and then mu nu. And then you could fix these two coefficients by imposing Jacobi relations with everyone else. Okay. But that one you probably should compute. Unless someone has a nice geometrical interpretation that I did not think about yet. Okay. One thing that you saw also was that this algebra was nothing but the Lorentz algebra in one higher dimension. So this was the same as the S, U1 plus 1, the Lorentz algebra. So you just have the more familiar algebra. And you can embed this, and these transformations are nothing but a Lorentz algebra in two higher dimensions. And you can even make use of this. You can generate some space that has two higher dimensions called the embedding space, act linearly on this space, and see what it implies for transformations on the D minus 2 on the D-dimensional space. And in this way, you can see that the nonlinear transformations, for example, K and so on, they are not more special than anyone else from the point of view of this Lorentz group. Okay? It also gives you some idea that the conformal theory wants to be related to something in higher dimensions, which is somehow related to AdS CFT, to the fact that this embedding space will be a very natural space. It is the space where we naturally want to define ante-de Sitter space. So you know that how do you define a sphere in 2 dimensions? It's very useful to go to 3 dimensions and say that it's the points in 3 dimensions uniquely spaced from the origin. If you want to define a D plus 1 dimensional AdS space, it's very useful to go to D plus 2 and define it as an hyperboloid in D plus 2. So like a pseudosphere in D plus 2. So even though in AdS CFT we want to go from D dimensions to 1 higher, it's useful to go to 2 higher to have some embedding space and then put there some pseudosphere which is anti-de-Sitter. So this is a very natural, very inspiring space when we will be discussing AdS CFT, but for now I will leave it in the back of our minds. And now we are going to explore the power of these relations here. Okay? Namely, what we saw was that this guy is a good correlation function. It obeys all the axioms that it should obey for a conformal field theory correlation function. Now we are going to do differently, and we are going to show that this is the only solution that we could write down. So this is the only correlation function in a conformal field theory. The only possible form for the correlation function. It's not what I wanted to do. Didn't I write something here already? It's there. Okay, very good. Okay, so it was. Okay. Any questions so far? No? Am I going too slowly? Okay. So we want to ask ourselves, what is the correlation function between an operator which has dimension delta 1 at some position x1 and an operator that has dimension delta 2 at some position x2? From now on, I will omit RD. It's always in RD. So now we are doing Euclidean flat space. Well, what do we know? We know that under a conformal transformation, so if you have this point x1, x2, under a conformal transformation, O delta 1 at x1 tilde, O delta 2 of x2 tilde is equal to omega to the minus delta 1 at x1, omega to the minus delta 2 at x2, correlator of O delta 1 at x1, O delta 2 at x2. But just by rotation by 180 degrees, so of course this should be the same if you just exchange x1 and x2. If you just exchange where is x1 and where is x2, if you just rotate the 2, you should get the same result. Okay? The correlation function should be invariant. Okay? So this should be just but this is inconsistent. I mean, I cannot have this correlation function be this one be equal to this one with different prefactors. So I cannot have this times this be equal to this times the same thing. So this implies that this correlator, let me call it G, this implies immediately that the only way this G is equal to 0 unless delta 1 is equal to delta 2. Okay? I cannot have this. It's immediately impossible unless the two deltas are the same. Okay, so the deltas are the same. And now I want to understand what's the correlation function. So it's already something that we learned, that we should always consider correlation function between two operators, OI of x, OJ of y, both with the same delta. Okay, what is this? So when we have some tilde, this is equal to omega of x, omega of y to the power minus delta, times the correlation function OI of x, OJ delta of y. Okay. Now it's very simple. Let's choose the simplest conformal transformation. just a dilatation. And let's denote this by a correlator, Gij, between at distance that only depends on the distance. This ought to be equal, then this is lambda to the minus 2 delta, times Gij of the distance x minus y. Right? Such that if we just choose lambda to be equal to 1 over x minus y, and denoting this Gij at distance 1 to be some real symmetric matrix. It's real by unitarity, but okay, some symmetric matrix Dij, just definition. Then we get immediately that our Gij at distance x minus y that appears on the right hand side is equal to some number Dij divided by x minus y to the power 2 delta. Okay? Which goes to delta ij under x minus y to the power 2 delta by just choosing a choice of basis that diagonalizes this symmetric matrix. So it's always possible to find the base of vectors that diagonalize this matrix Dij, such that at the end of the day, the correlation function Gij is just delta ij over x minus y to the power 2 delta. This is an extremely important result, or let's put here delta I to indicate, okay, no, it's okay. Okay? Okay, so the conclusion that definitely deserves a box is that OI of x, OJ of y, you can always find the base of operators such that all you have is a power law with some coefficients delta I, which are called the dimensions or conformal weights how do I write weights? GHT? GTH? Weight? Come on. GHT or GTH? No one knows?
HT.
HT, very good. I always confuse. That looks right. Or conformal weight, or conformal. Very good. This is something extremely important. It reduces, you must keep in mind that this is a huge achievement. In a quantum field theory, to compute two-point functions, it's almost impossible. And here, in conformal field theory, we see how drastic the simplification is. The computation of a two-point function is reduced to the computation of a number. You want to compute a correlation function, you have to compute what is the number delta. It's an exponent, the critical exponent. It's a huge simplification over a quantum field theory where you have a ton of scales and where you have very complicated behavior. So these are critical exponents if you want. And this is basically what most people are interested in. By most people, I mean, say, experimentalists that study critical phase transitions in the lab by studying boiling water or spin systems and so on. What people typically measure is critical exponents. For the most part, people focus on two-point functions. it's not that common. Very, very, very little is known about higher point functions. Really, this is the main, the fundamental, the simplest and the most important object, if you want, that is more directly related to what people measure and what people study, is really the spectrum of a conformal field theory. Okay, so another name for this set is the spectrum of the conformal field. Now, this spectrum reminds you kind of energies, not of dimensions. And it's good that it should remind you of energies because it's exactly what it is. But this we will see tomorrow. So we will see that it's not just a question of name. So it is related to correlation functions in RD. So this is about, okay, let me write once more. This is in RD. But you will see that what is the interpretation? How should I think if I put my theory, say, on a cylinder, on the sphere times time, where I have like a closed space times time? And you will see that in that setup, the way to think about these deltas, they are the energies of your CFT states, of your quantum field theory in this sphere. Okay? It's something that it should not be totally surprising if you look at the result. If you look at this expression here for the computation in the cylinder, you see, when tau minus tau prime is very large, this behaves as e to the minus delta times tau minus tau prime. That goes, remember this is Euclidean. So if you change tau to it to make this tau a time direction, this is e to the I delta t, which should look familiar. It starts to smell like some energy, where this delta is playing the role of some energy, and we will make this precise tomorrow. Okay, very good. So, as I expected, I would by now be way beyond time. Okay, I want to make a further comment. This was one derivation of two-point functions, but there is another derivation. Okay? The other derivation, which, of course, technically it will end up being the same. But another wording that I could attach to this derivation is the following. I could say, first of all, I could first argue that whatever I'm going to write, the result is unique. Okay? So how could I argue that the result is unique? Because I can argue that any 2 points, I can relate them by a conformal transformation to points that say 0 and 1. Right? Because imagine I have any 2 points in the space. Okay, first I can do a rotation such that they are along the x-axis. Then I can translate such that one is at 0 and one is at some point. And then I can make a dilatation such that they are at 0 at 1. So it's clear that just by a sequence of conformal transformations, I can always, whenever I have 2 points, map them to 0 and 1. Right? But then I know how to move from any points to others by conformal transformation. So I can write 0 and 1 to be one parameter, which is what I did here. I call it dij. And wake up the correlation function, generate any possible correlation function by just applying a conformal transformation. That is, I just find what conformal transformation maps 0, 1 to xy, compute the corresponding omega factors, and apply the formula there. And whatever I get must be unique. It is the solution. But once I realize it is unique, all I have to do is check that this is invariant under inversion, and I'm done. Okay? So once in my mind I realize it is unique, all I have to do is check. Is it clear? Now let's use then this logic for 3-point functions. Let's now think about 3-point functions. Okay, let's repeat this argument. 1, the answer should be unique. It should be unique because we can always map 3 points to any 3 points. Anywhere we want, like for 2 points. For example, the conventional one we always do is 0, 1, and infinity, but it can be 0, 1, and 2 if you want. Any 2 points. Again, let's try to see this. So please, I don't want to write everything, so just follow and then watch it on Pearson and copy if you want. So you have 3 points, okay? So let's try to put them at 0, 1, and infinity, for example. Okay? So let's try. So we have 3 points somewhere. So let's see. Let's see if I can do it. Okay, first thing we can do is, let me think a bit. I should have prepared. Okay. First thing we can do is make a translation such that one of them is at 0. Now do an inversion. That goes to infinity. And now that one is at infinity. Now make a rotation such that the other two are aligned along the x-axis. The one at infinity continues at infinity. Now translate these two such that one is at 0, one is at some position, the other is at infinity. Now make a dilatation to put the one which was at x to be at 1, for example. Okay? So this time we have to use inversions. It was crucial to use inversion. Without inversion, we couldn't have done it. It was very useful to have this trick where you start with 3 points, put one at 0, and send it away, and now start doing whatever you want, and it stays there, and so on. Very crucial. Without inversion, we'll be done. So here, we are really exploring conformal group. We are not exploring just scale invariance or something. Inversion is crucial in this derivation. Okay, so we can map it. So now I'm going to write an ansatz, and then we check whether it is okay or not. Okay? Another way of doing it would be following the same kind of logic, but it just takes a few more time and we gain nothing conceptually, so I'm just going to tell you what the result is. I just want to see because I wrote here in a slightly different way than conventional. Okay. So we just need to check that the following result is invariant under inversion. OI of x, OJ of y, OK at position z. It's equal to 1 over x minus y to the power the dimension of the guy at x plus the dimension of the guy at y minus the dimension of the third guy. And then the same thing for the other guy. So x minus z, dimension of the guy at x, plus dimension of the guy at z, minus the other one. And then y minus z to the same thing. Dimension of the guy at y, plus dimension of the guy at z, minus dimension of the guy at x. Now, we already chose our normalization to fix the 2-point function. We don't have the right to normalize now the 3-point function. Whatever is here would be a number c, I, j, k. Recall that under inversions, if we want, we just need to check inversions. Under inversions, x minus y squared goes to x minus y squared over x squared y squared. So if you apply it to the denominators, let's see what power of x squared we get. Let's just do x squared. X squared comes with this plus this minus this, but then it comes with this plus this minus this, so everything cancels except delta I. So you get x squared to the power delta I. Is it clear? Because you get x squared to this power, and you get x squared to this power, and the delta j and delta k cancel, and you get delta I. So indeed, you get what you expect. You get x squared to the delta of the first guy, and so on for the second, and so on for the third. Is it clear? So it's invariant under inversion. It's Poincare invariant. We are done. It's conformal invariant. So it's the unique result. Okay. Any question? Let me just maybe make a comment here. Okay, a comment. Conformal invariance was crucial. So just scale invariance would tell you that the correlation function between these operators, g, I, j, k, would be given by anything that would be of the form x minus y to the a, y minus z to the b, x minus z to the c, any number of terms with some random function c, a, b, c for the operators I, j, k, provided a plus b plus c is equal to delta I plus delta j plus delta k. So it's a huge constraint that conformal invariant maps you from an infinite space of solutions where you could basically write almost everything to just one particular term in this infinite sum that you could write. It's a very, very tight constraint. Okay? So when you do, say, Monte Carlo simulations on the Ising model, and you check, say, 3-point functions, and you want to ask if the Ising model at a critical point, is it conformal invariant or scale invariant, a very useful check you can do is check the 3-point function. I mean, but actually it's a pity, because people, what typically they do is they put a point at 0 in the lattice, they put one at r and minus r, and then they just check dilatations under r. In fact, all this would work, and there is a very nice check of conformal invariant that people never do. But okay, that's life. Okay. What about, so we are learning about, tomorrow we will spend lots of time on the 2-point function. We'll kind of go back. But today I'm choosing to discuss these kind of technical details about higher point functions just because they are kind of simple technically and also important. So what about 4-point functions? Now, for 4 points, symmetry is not enough. Symmetry is not enough. If you cannot map 4 points to whatever you want. You cannot. It's easy to see that what you can do is the following. Imagine we have 4 points, and I focus only on 3 of them, and do the same game that I did before. Okay? So they will end up 1 at 0, 1 at 1, 1 at infinity. And now the 4th one is floating here somewhere. Right? So of course something I can do is rotate this with respect to these x's and put it in the plane xy. Okay? So I can parameterize all 4-point functions by the position of the 4th point. If I put 1 point at 0, 1 point at 1, and the other at infinity, then there is a point here, if I consider this the plane x and y, a point here, typically we call it, I don't know if this is x2 or whatever, I don't know. I always forget which one is more convenient to use. I think it's x2, but let me see 1 second. So we cannot choose them wherever we want, so there is dependence on the position of this 4th point. Yeah, point x2. I chose point z to be x plus iy. So this is related to the point, the coordinates of the point x2. Okay. And I could define z bar to be x minus iy. And I cannot, I mean, now by any, you can easily see that if I fix 0, 1 at infinity, roughly the only thing I can do is take it out the plane, but that I don't want to do. There's nothing I can do. This is now a parameter that I cannot just fix by symmetry the dependence on this z. Now, there's a more canonical way that people typically use to explain this, which is the following. If I consider, can you read if I write here? No? Yes? No? So, so let's write a correlation function between 4 operators. Let them be the same. All have the same dimension delta. Then you can easily see that you can write something that is invariant under inversions. You can easily write, you just write x1 minus x2 to the power 2 delta, x3 minus x4 to the power 2 delta. And And you can easily check that under inversions, this transforms as a 4-point function should. But now you can write this multiplied by any function of stuff that is Lorentz invariant and invariant under inversions. And there are two things you can write, u and v, that are called cross ratios, where you define as x1 minus x2 squared times x3 minus x4 squared divided by x1 minus x3 squared, x2 minus x4 squared, and a similar one for v that you write as x1 minus x4 squared, x2 minus x3 squared, divided by the same denominator. So these cross ratios, u and v, they are invariant under inversion. Is it clear why they are invariant? Because you see, this guy picks a factor of x1 squared, x2 squared. But there is a factor of x1 squared coming from this guy, and there is a factor of x2 squared coming from this guy whenever I transform. So they cancel out, and similarly for all the other factors. So these guys are invariant under inversions, and I think you actually showed it yesterday during the tutorial that they were invariant under all conformal transformations, which is very clear because from the embedding coordinate, they are just ratios of Lorentz products. So what you will have, this is something dynamical. Okay? So this is something dynamic. This is very theory dependent, of course. It's a very interesting object that, of course, there's no universality here. So different theories have different physics, and the way you compute this correlation function of 4 points, this will change a lot. Okay? And there is a simple relation between these parameters u and v and this nice geometrical interpretation where I fix 4 points and I parameterize the last one. If you plug those points inside this u and v, those points there, you find that u is equal to just z times z bar, and v is just 1 minus z, 1 minus z bar. I think it's more or less obvious, you see. x1 minus x2 is the distance from the origin. That point is at z, so the distance from the origin is just z bar. And x1 minus x4, or x2 minus x3, rather, is the distance from point 1. And that is 1 minus z times 1 minus z bar. And the other factors, you can easily see that they just drop out. Very good. This was all that we did right now was for scalars. So far, all I did is, I never introduced indices. They were all scalars. We never considered Maxwell vector fields, nothing. Everything was a scalar. And actually, during these lectures, I will almost always consider just scalars. But let me make a few comments about higher spin operators. Okay? So we could have some operator OA in some non-trivial representation of the rotation group. It can be a vector, a scalar, Fermion, whatever. I could have a non-trivial object. Then you might ask, what about a correlation function OA, OB? Okay? So, okay, I'm not going to go through the analysis, but it's more or less a generalization of what I've done, and this is contained. I can give you some references if you want to study this in more detail. But I just want to tell you that you can do it. This guy is also fixed by conformal symmetry. You can compute correlation function between OA and two scalars. This guy is also fixed. But you can start asking more complicated stuff like OA, OB, OC. And this is given by a sum of some tensors now, which A, B, C. They depend on I, J, K. Also the three operators, but now on the tensor structure as well. It's not just a number like this C, I, J, K. And then there is some space dependence, x minus y to some power, There is some space dependence that is fixed. But in general, you've almost fixed the result by conformal symmetry. There is a sum over Q, but what's important to emphasize is that this is a finite sum. So there are finitely many tensors compatible with conformal symmetries. You can analyze them all. You can make a catalog of all the possible tensor structures. And this is a finite sum, and these guys are known. The tensors are known, so you have Q numbers to fix instead of a single number. Okay? So in general, if you want to compute 2 and 3-point functions in a CFT, okay, the set of parameters delta I and these 3-point functions C, I, J, K that could also depend on some Q if we are considered tensors and so on. Okay, these guys, they determine all 2 and 3-point functions in a CFT. But more than that, they determine, and this is not obvious at all now, but I want to announce it, all correlation functions. So I said that this f was a typically new function, dynamically, that is theory dependent. I'm telling you that somehow it is possible to construct this object if you just know if you know the full set of deltas and 3-point functions, not 1 or 2. All sets of deltas and 3-point functions in your conformal field theory. And because of that, this is a very important set, a very powerful set of numbers, and this is what is called the CFT data. For its conformal field theory, instead of giving a Lagrangian, if I can choose, what do I prefer to study a theory, a Lagrangian or this set of numbers? I prefer that set of numbers infinitely more. This is really much better. And this is like a definition of a CFT as well. It also defines, as we'll see, the CFT. So if someone offers you the Lagrangian or this, don't hesitate. I mean, this is way, way, way better. But this we will see later. So for now, I think the first statement is clear, that 2 and 3-point functions are totally determined by symmetry. It's of course not obvious why we can determine higher point functions by this CFT data. And this we will see tomorrow. So what we will do tomorrow is 2 things. So we will start exploring, okay, what do we know more about 2-point functions, these deltas? What's the physics of these deltas? How are they related to energies? If they are related to energies, can we learn something from them, from unitarity? Do these energies need to be positive? Can we start learning something about these dimensions and so on? And about this physics of this map between flat space and the cylinder and so on? That's one thing. And now that we are starting to play with all these different space-times and starting to see this Lorentz algebra in higher dimension, I also want tomorrow to give some kind of appetizers towards AdS CFT and start playing. Okay, we are almost ready to start introducing some space-times that at this point are begging to appear, which are natural extensions of these spacetimes with one more dimension, that we already have some familiarity with many of these transformations. Okay, that's what we are going to do tomorrow. Any question about today? Was it too fast? Too slow? Is it clear? Any conceptual question in general about where we are going? And I cannot promise I can answer that one. I would have to know what I'm going to do later, but okay. I have some idea. No? Okay, I'll see you tomorrow.